Present here today to talk about the application of linear system, which stand at the very core of science and engineering. Linear systems are not abstract mathematical notions, but powerful tools that enable us to model, analyze, and solve a whole variety of problems. Everything from small-size quantum mechanics to large-size system of traffic network. Linear systems provide a framework in which consistency may be drawn between understanding and innovation. Scientists and engineers over the country have used linear systems to explain natural phenomena, optimize process, and build revolutionary technologies. They reduce complexity into comprehensible forms to allow solving otherwise insurmountable problems. In this presentation, I look into the application of linear systems across wide fields such as physics, chemistry, biology, electric and mechanical engineering, civil and aerospace engineering, and computation method. Along the way, we will highlight real-world application and future trends that make this topic so exciting. First one, I will like to talk about linear system in physics. Physics offers some of the most intuitive application of linear system as they help describe and predict natural law that govern the universe. Machinic in equilibrium linear systems are crucial for resolving machine issue. Newton's second law, F equal ma equal ma, is a cornerstone of classic mechanics. For instance, in static, the use of linear equation enable an engineer of computed force in trusses or beam to ensure that structure under load are stable. The principle in key in designing bridge, skyscraper, and other infrastructure in dynastic linear system help predict how objects move under the influence of force. For example, automotive engineers use linear system to optimize substation system, ensuring a smooth and safe ride for passengers. For the design of robotic arms and trajectory calculation, robotics also heavily depend on linear mechanics. Next one is electromagnetism. The Maxwell equation, which describe electromagnetism, are classical example of linear system in action. In case of linear media, such as certain type of dielectric and magnetic material, this equation reduced to linear models. Models in these forms are utilized in antenna design and electromagnetic sensors, among other wireless communication devices. For instance, mobile phone signal transmission depend on linear electromagnetic equation to ensure that signals are clear and uninterrupted. Similarly, to design of MRI machine, leverage linear electromagnetism to create detailed image of the human body. Next is quantum mechanics. Quantum mechanics is a branch concerned with the study of the behavior of particle and at atomic and subatomic level, and the influence of linearity is very profound within the subject area. The Synodiger's equation, describing how a quantum state evolves in time, is a linear particle differential equation. Solution to this equation have enabled the prediction of atomic energy levels. Characteristic of chemical bond and semiconductor behavior, these insights have also given rise to revolutionary technology, including laser transistor and quantum computers. Quantum mechanics, for example, enable the design of semiconductor used in microchips, which power everyday devices used by people. Next page is saying linear system in chemistry and biology. Linear system finds science fiction application in modeling as well as solving problems in chemistry and biology. First one is chemical equilibrium. Linear system in reaction engineering provide the concentration of reactant and product at equilibrium condition by utilizing stoichiometry and principle of mass composition. And engineering may model complex chemical reaction seeking to maximize use and minimize waste. Ammonia production via the Haber process illustrate the use of linear system in balancing reaction conditions. Such a calculation will ensure maximum efficiency that, if applied in large-scale industrial production, could save energy and resource. Next one is spectroscopy. Spectroscopy is the interaction of light and matter, and it relies on linear algebra in analyzing data. Various techniques such as Fourier transforms enable research to disconvolute signal and identify chemical composition or impurities within material. These are now common methods of research for environmental science in measuring air and water quality, and in the pharmaceutical fields with the analysis of drug formulation. Next one, population dynastic. In biology, linear systems are used to model population dynastic. For example, the Leslie metric model predicts the change in population over time, taking into account factors such as birth and death rate. This is vital for conservation biology, where such models inform effort to protect endangered species. As an example, for analyzing the population data of pandas, conversations are able to put resources into action for better breeding program and habitat preservation. Number four is neutral network. Computation neutral science model neutral behavior using simplified neural system. Truth modern artificial intelligence is based on non-linear system. The basic of neutral network is based upon linear transformation. This model help explain how neutrals process information and are connected with each other. Linear systems also play an important role in the training of machine learning algorithms where the weights and bases are optimized iteratively using linear methods such as gradient descent. Next page is saying application in electrical and machinery engineering. Engineering fields are perhaps where linear systems find their most practical and wide-ranging application. First one is circuit analysis. In electrical engineering, Kirchhoff voltage and current rules from the basis for any analysis involving electrical circuit. All of these systems use linearly related equations describing the current and voltage relationship throughout various circuit components. For example, in designing microprocessor or power distribution system, engineers use nodal or mesh analysis to ensure that circuits operate efficiently. Linear systems also form the basic for advanced technologies, including renewable engineering grid, which integrate solar and wind power source. Number two, signal processing. Linear systems are the backbone of signal processing, which encompass everything from communication to audio engineering to medical imaging. Convolution filtering and Fourier transforms are only a few of the technical applied to graduate that the signal transmit accurately, are received accurately, and are correctly interpreted. As a specified example, for telecommunication, linear system optimize data transmission across network, such as 5G implementation. MRI machine use signal processing to reconstruct clear image from raw data. Next one is structure analysis. The Sidnus metric method by structure energies is employed in analyze how the force are distributed across the structure. This linear method help graduate that buildings, bridge, and other infrastructure withstand external stress while maintaining structural integrity. A notable example is in the construction of earthquake-resilient buildings. The energies make a simulation of seismic force using linear system to predict how structure will respond during the occurrence of natural calamities for safety purpose. Last is the vibration. The study of vibration in machine system often involve the eigenvalue analysis, which is a core concept in linear algebra. It helps is determine natural frequency and mode shape, important for noise reduction and prevention of machine failure. Application to vibration analyzed by aerospace engineers help in the design of quieter aircraft engines. Automotive companies use this principle to reduce noise in engines and enhance passenger comfort. Last, thank you for all your attention. Now I will hand over my group member who will present the remainder of the slide.
Today I want to talking about the applications of linear systems. First, thank you for my partner's introductions. I will start my presence for the remaining slides. I will talk about the civil and aerospace energy applications. First, let us talking about the linear systems. These systems also play a pivotal role in civil and aerospace energy, where large-scale systems require process modeling. First, finite element analysis is called FEA. Finite element analysis is a computational method that discretes structures into smaller elements, which presents as linear equations. By solving these equations, energies can predict stress, strain, and deformations under various conditions. This technique is indispensable for designing bridges, tunnels, and skyscrapers, ensuring they can withstand loss and environmental force. The next example is the traffic energy. Urban planners use a linear programming model to optimize traffic flows and reduce congestions. These models analyze network flows, enabling planners to design efficient transportation systems. For example, in cities with a growing population, traffic optimization models help allocate resources for new roads, traffic signals, and public transport systems. The next example is the flight dynamics. In aerospace energy, linearization techniques reduce complicated flight equations to the form that energies can use to study stability and control. This makes aircraft fly safely under different conditions. For example, autopilot systems use linear models to maintain steady flight paths even in turbulent conditions. The next example is the structural mechanics. Linear elasticity theory is used to model the deformations of materials under stress. This is crucial when designing lightweight yet strong components in aircraft, spacecraft, and automobiles. For instance, in aerospace, engineers model the wings of the aircraft use a linear system to ensure their structure can bear the force during flight. Computational methods for linear systems. The size of many problems today necessitates is the use of computation tools to solve linear system efficiently. First of all, detect methods. The technologies like gases elimination and LU decomposition provide extra solution to linear systems. These methods come in handy in fields such as the structural energies and physics where precision is vital. The next example is the iterative methods. When the systems are larger, iterative methods such as Jacobic and conjugate condition are used. The aforementioned technology can rely on simulations regarding weather forecasting, fluid dynamics, and other computationally demanding areas. The next is moving forward. Let the differ into the engagement problems, which are the paramount importance in discussions such as structural dynamics, quantum methods, and data science. These problems enable us to uncover the fundamental properties of linear systems by identifying their eigenvalues and eigenvectors. Technology like the powers interactions and QR or gradients are essential tools for stability analysis and model decompositions. By employing these methods, we can extract critical insights from linear systems such as the protecting systems behavior, determining natural frequencies, and simplifying complex data structures. This deep understanding allows us to design more stable structures, analyze quantum states more effectively, and define meaningful patterns from vast data sets. The next is a software tool. Modern tools such as NATLAB, mathematics, and libraries in Python make the solving of linear systems within reach of the energy and researcher. These tools streamline the process, enabling faster experimentations and prototyping. Research and development application linear systems are driving innovations into research and development. First are the optimization. Linear programming can be used to optimize resources across different industries, including logistics and manufacturing, for example. This technology is used by companies in minimal cost while at the same time meeting production targets. The next is the data analysis. Linear regressions and least square fitting are cornerstones for the analysis of the experimental data. Seeking out trends and prediction, the techniques listed above have a wide range of applications from economics to consumer science. The next is simulation. Many simulations use linear or process measures to model complex systems. Examples include climate modeling, where linear systems are used to simulate automatic behavior in order to gain insights into global warming trends. In the end is the conclusion. Concluding linear systems represent something of the backbone to science and engineering. The simplified complexity giant realize solution and further incredible performance. Applications vary across disciplines from an understanding of the quantum world to traffic system optimization in big city. Further ahead, the interface of linear systems with machine learning and spontaneous computational techniques will open up many exciting properties. The journey of discovery and innovation driven by linear systems is far from over. Quite literally, the potential is without limit. Thank you.